In this lecture, let's try to wrap up the remaining Laplace transform properties. We will start with the frequency shift property of Laplace transform. So suppose we are given that a time domain signal f of t has a Laplace transform of cap f of s and a region of convergence defined as cap r. Then if we have a frequency shift by s sub 0, where s sub 0 is some complex number, and we can define this as sigma 0 plus j omega 0, then what happens in the time domain is actually a multiplication by e to the s sub 0 t. Now this should look very similar to the frequency shifting property of the Fourier transform, where when we shifted in the Fourier domain by omega naught, in the time domain we multiplied by e to the j omega naught t. Now, when we shift in frequency, the region of convergence actually gets shifted as well. Let's take a look at that in a little bit more detail with an example here. Let's suppose we are trying to find the Laplace transform of e to the negative 2t u of t. We have already done something similar in a more generic manner before, but we are trying to apply the frequency shift property along with an earlier result to get this. So from earlier, we know that the unit step has a Laplace transform of 1 over s with one pole at origin, and the region of convergence being real part of s greater than 0. So all of right half of s plane, excluding the origin, excluding the vertical axis, because that's where the pole is. Now, if we use this earlier result for the Laplace transform that we are trying to find, u of t needs to become e to the negative t u of t. So essentially in the time domain, we are multiplying by the factor e to the negative 2t, which means now we can use the frequency shift property here. S sub 0 is actually just negative 2. So in the s domain, we are going to replace s with s plus 2. So 1 over s becomes 1 over s plus 2. Earlier, ROC was greater than 0. Now with this, the region of convergence is going to be sigma greater than negative 2. And you can use that earlier result of e to the negative at u of t to validate this example. So that's your frequency shift property. Shift by s sub 0 in the s domain, multiply by e to the s sub 0 t in the time domain. ROC also gets shifted. The next property that we are going to look at is the time reversal property. So what happens in the Laplace domain when you flip the signal about the time, about the vertical axis? So if given f of t has a Laplace transform of cap f of s and a region of convergence as cap r, if we do a time flip or a time reversal of this time domain signal, then in the Laplace domain, it also gets flipped about the vertical axis. And ROC is the flipped version of the earlier region of convergence. Let's take a look at an example here. We are trying to find the Laplace transform of u of minus t. So we took a unit step, we flipped it about the vertical axis, and we are trying to find the Laplace transform of that. We know from earlier that u of t has a Laplace transform of 1 over s and a region of convergence as a real part of s greater than 0. All of the right half of s plane, excluding the vertical axis. And u of minus t, using the time reversal property, its Laplace transform will simply be f of minus s. So all the s's will need to be replaced by minus s, giving you the result minus 1 over s. And the region of convergence for this is going to be flipped version of the earlier region of convergence. So now the region of convergence is going to be real part of s less than 0. So that would be all the left half plane of left half of the s plane. Let's take a look at the time scaling property. So what happens if you do a compression or an expansion in the time domain? So again, we start off with the given time domain signal f of t, whose Laplace transform is defined as cap f of s and a region of convergence defined as cap r. And then if we scale the signal in time domain by factor a, so if we have f of at, and depending on whether a is greater than 1 or less than 1, it's above 0, because that would mean that we are using, if it is less than 0, that would mean a time reversal property, which is not what we are discussing right now. So if we are between 0 and 1, that would mean a time compression. If we have f of 5t, f of 10t, and so on, that would mean an expansion. Now, if we scale in time domain, that would mean that in the Laplace domain, we have 1 over absolute of a, f of s over a. So we do something that is reciprocal in the s domain. This essentially means that if you compress the signal in time domain, things are going to be changing faster, which means that there are going to be more high frequency components, which means in the s domain, things get expanded, and vice versa. The region of convergence is going to be a scaled region of convergence. So if earlier it was R, now it is going to be AR, where A is the time scaling factor. Let's take a look at this property with an example. We are trying to find the Laplace transform of e to the negative 2t u of t. So we cannot directly apply the time scaling property because it is not e to the negative 2t u of 2t. But it turns out u of 2t and u of t are the same signal. So if we start off with a known result, which is e to the negative t u of t, the Laplace transform is 1 over s plus 1, and a region of convergence here is real part of s greater than negative 1, then e to the negative 2t u of t, which is the same as saying e to the negative 2t u of 2t, they both get on at time 0. And for time greater than 0, they are 1. For time less than 0, they are 0. So u of t and u of 2t are essentially the same signal. So for this, using the time scaling property, we can write the function in the Laplace domain as 1 over absolute of 2 multiplied by 1 over, instead of s, now I have s over 2 plus 1. And the region of convergence here is going to be real part of s over 2 greater than negative 1, which essentially means sigma should be greater than negative 2. So that's how it is getting scaled in the S-plane. So the region of convergence changes, and the Laplace transform also changes by 1 over absolute of a, f of s divided by a. Let's go on to the next set of properties here called derivatives. So they include both a derivative in the time domain or a derivative in the Laplace domain. We start off again with a given time domain signal f of t, whose Laplace transform is cap f of s, and a region of convergence cap r. If we differentiate the signal in the s domain and an additional negative sign, that is equivalent to multiplying by a factor t in the time domain. These are all Laplace transform operators. And the region of convergence doesn't change when you differentiate the signal in the S domain. Or when you multiply the time domain signal by t, the region of convergence doesn't change. However, if you were to differentiate the signal in the time domain, that would correspond to multiplying the Laplace function with s. So it becomes s times f of s. And the region of convergence here is at least cap r. So it could be more than that, but it is going to be at least r. And this statement can quickly be verified by considering the region of convergence of u of t and the region of convergence for an impulse function. For u of t, our region of convergence was real part of s greater than 0, and for an impulse, it was all of s plane. All of s plane. So essentially what this means is when you differentiate the signal in time domain, your region of convergence expands, gets bigger in the S plane. Now, another note over here, as you keep differentiating the signal in time domain, the second derivative, third derivative, and so on, you will keep multiplying the f of s, the function in the Laplace domain, by an additional s. So you get s squared, s cubed, and so on. All right, now let's try to solve an example over here. We have a finite duration signal, f of t. So we already know that its region of convergence is going to be all of s plane. Let's try to find the Laplace transform for this. So first we'll begin with writing f of t in terms of unit steps. So here I'm going to have two pieces. One is that line over there, which is essentially slope 1 and passes through origin, so y-intercept is 0. So t multiplied by a gate function which opens at 0, closes at 2. So you've got u of t minus u of t minus 2. And then I need to add another linear function which is also gated to this, the blue line. So it is going down, so the slope is negative, right? So the slope is negative, and dy over dx is 2 divided by 1, so 2. The function is time. The y-intercept is going to be, so if I backtrack from here, between 3 to 2, it went up to 2. Between 2 to 1, it would go up to 4. Between 1 to 0, it would go up to 6. So I can say 2t plus 6 here. And then I can come back here and say negative 2t plus 6. And I have a gate function between 2 and 3. So open the gate at 2, close the gate at 3. Now I've written the function in terms of unit steps. I'm going to try to use my time derivative property to solve this problem. So if I differentiate the function in time domain, t u of t would become u of t. Negative t u of t minus 2 would simply become negative u of t minus 2. And then from the other piece, I have negative 2 times u of t minus 2 minus u of t minus 3. And in fact, I can differentiate it again so that I get an impulse or bunch of impulses. So if I differentiate it a second time in the time domain, I have, dt squared. Delta u of t will give me a delta of t. I can combine u of t minus 2, so I have negative 3 u of t minus 2. So that differentiated will give me negative 3 delta of t minus 2, and then plus 2 delta of t minus 3. Now I can quickly go to the Laplace domain. So let's do that in blue. So when I've differentiated the signal twice in the time domain, which essentially means I multiply by s squared in the Laplace domain, which equals the Laplace transform of an impulse 1, Laplace transform of 3 delta of t minus 2. So that is 3, and using the time shifting property, we can say e to the negative 2s and plus 2, and then again using the Laplace transform of an impulse as well as the time shifting property, we can say e to the negative 3s. And then now we just simplify to rewrite the function in the s domain, in the Laplace domain, as 1 minus 3 e to the negative 2s plus 2 e to the negative 3s divided by s squared, and our region of convergence is going to be all of s plane, all of s plane. And the reason for that is that the signal is finite duration, so it is only existing between 0 and 3. All the other places it is 0, which means that it is integrable and it is square integrable. So it's going to converge in all of S plane. All right. This was a short video to recap some of the properties, and in another video we will continue with properties of the region of convergence.